Okay, we're back. We're doing part 3, right? So now we talked about what a chemical reaction was. So now we're going to talk about things that affect the rates of chemical reactions. Oops. There we go. Okay, so what are some things that affect the rate of a chemical reaction? So we'll talk about 3 things: temperature, substrate concentration, and catalysts. Okay? Temperature is, of course, a measure of heat. Heat's a kind of energy, and heat is the energy from the random motion of molecules, right? As you warm things up, molecules are moving faster and faster and faster and faster and faster. As you cool things down, they're moving less and less and less and less and less. Okay? So, you put the pot of water on the stove, you turn on the stove, the heat, of course, heat flows from hot to cold. So the heat flows from the fire or the whatever, let's assume it's a gas range. The heat from the fire flows into the pot, which flows into the water, okay? That water starts to heat up, so those water molecules, the water is liquid, the water molecules start moving, right? They're always moving, but now that as the temperature increases, they start moving faster and faster and faster. Eventually, they're moving so fast that they kind of fly apart from each other, and you go from being a liquid to a gas. Okay? And then, of course, you do the opposite. You take the pot of water and you put it in the freezer. Well, suddenly the air is very, very cold, and heat flows from hot to cold. So, the room temperature water on the stove, the water was the cooler thing, right? So heat flowed into the water. The room temperature water in the freezer, now the water is the warmer thing, so the heat flows out of the water and it flows into the air, right? And that's why the water molecules start moving less and less and less and less and less. Eventually, once it hits 0 degrees Celsius, the water molecules kind of get fixed in position. Now, they still kind of like wiggle and vibrate, but they don't actively move anymore, and that's when you go from being a liquid to a solid, right? And that's why, like, if you're storing food in the fridge or you're putting something in the freezer, you shouldn't put something super hot into the freezer right away, right? If you make a huge bowl of soup and you stick it in the freezer, it's going to basically warm up, if there's enough volume of something hot inside your freezer, it's going to warm up your freezer and and so other things are going to start thawing. That's why, you'll read things about, you making soup or you making whatever. They'll say, let it cool to room temperature and then put it in the freezer or in the fridge. Okay, so that's a long way of saying as you increase the temperature, molecules are going to move faster. Well, the way chemical reactions work is that these reactants, these starting material molecules, they basically have to bump into each other. So if they're moving faster, they're more likely to start bumping into each other. So generally, the warmer it is, the faster chemical reactions work. And if you made a graph, you would have a basic pattern of something that looks like this, right? Where the warmer it is, this would be, this would be temperature. This would be rate of the reaction. And you could see, as it gets warmer, the reaction rate increases and increases and increases. And then you get to a stage here where suddenly it decreases. Usually because at this point, it's so warm that things start breaking down, right? And of course, where this thing drops off will just depend on the reactants and the conditions and a lot of things. Okay? Substrate concentration is another one, right? Substrate concentration means how much of those let's say, substrate, let's not call it substrate. Let's call it reactant. That's a little bit more general, okay? Substrate would be if we're referring to enzymes or reactants more general. So let's use that term. So reactant concentration, right? So remember, these are the reactant molecules here, your starting material. So if you increase the reactant concentration, the more of these molecules you have, again, just makes sense, they're more likely to run into each other. So if you increase that reaction, it's going to increase and get to a point. Now, unlike this one where at some point it'll just start breaking down, usually it reaches a point where it gets sort of a saturation point and then it just doesn't go any faster, right? Chemical reactions happen there. I mean, they don't happen at infinite speed. So there's going to be an amount where they're going to have to bump into each other, and they're going to start, so past a certain concentration, you're not going to see an increase, or the level of increase is so slight you barely notice it, right? there will be sort of a saturation point, but it won't ever just completely stop. Not usually, and there are always exceptions. Okay? Third things are catalysts. Now, catalysts are important. You know, catalyst is a general term, is defined as anything, any substance that speeds up a chemical reaction, right? So catalyst basically helps chemical reactions go forward. The important thing about catalysts is that they're not reactants, okay? So, not reactants, right? So that means they're not consumed by the reaction. Why did I say cane? That's what happens when you don't proofread, right? Okay? So they're not part of the actual reaction itself, which means you can reuse catalysts over and over and over again, okay? And that ends up being important because your cells have all kinds of chemical reactions that are happening inside your cells all the time, right? And these methods here of temperature and reactant concentration, these things often aren't viable ways of speeding up those chemical reactions to get them happening at a reasonable pace, right? And so your cells are going to use these biologically derived catalysts. They're called enzymes. We have a whole chapter on enzymes, so we'll talk about them a whole lot. But enzymes are essentially biological catalysts, and they help speed up chemical reactions in your cells. Your cells have thousands of chemical reactions that happen inside of them, and virtually every single one has its own dedicated enzyme to help it move forward, right? A lot of the reactions would, without the enzymes, the reactions would happen, but they would happen at such a slow pace that really it wouldn't be very relevant to the cell. But by having the enzymes, you can speed up those chemical reactions. Sometimes you can make chemical reactions, something like millions of times faster, so that they happen at a rate where it makes sense. Okay? And we'll talk lots of examples about enzymes and catalysts and all that stuff in the future. So you'll see this again and again and again. All right. The next part of the chapter is kind of a switch in gears, and we're going to talk mostly about water and properties of water. Okay? So here's water. There's some pictures of things that are involving water. Let me scoot this over. Give myself a little bit more room. There we go. Okay? Water is interesting because... Sorry, swallowed wrong. Water is interesting because it exists in sort of the three common states of matter, solid, liquid, and gas, right? And you have other states of matter, plasma and different kinds of plasma, but the three standard ones are solid, liquids, and gas. And water exists in those three states, on the surface of the earth, at all times. I mean, it's one of sort of the criteria for looking for life on other planets. Life as we know it. Now, of course, we don't. The universe is a huge place, so there could be some completely different life forms that are based on completely other forms of chemistry. We just don't know about it. But as far as we know for life, you have to have temperatures where you would have solid, liquid, you'd have to have these different states of water, right? You have to have liquid water and, gas and all that stuff. So, of course, solid water is ice. This is a nice glacier, which is just a giant ice cube. Liquid water, this is an ocean. This particular thing is living inside of it is a mako shark, very cool looking shark. And then, of course, steam, gas. Okay? All right, cool. So water, as we know, is H2O, and water has a lot of properties, and we'll talk about these chemical properties of water. That's what we're talking about now. And what gives it the properties is that water is what's called a polar molecule. So let's talk about what that is. Okay? So water is highly polar. What that means is that it has an uneven charge distribution. So remember, as we said before, a water molecule, the hydrogens are covalently bonded to the oxygen, right? So the atoms are the electrons are sort of whizzing around the whole thing, right? It's not as if the oxygen electrons hanging around the oxygen and the hydrogens hanging around the hydrogen. All of the electrons kind of, go around the whole thing. Okay? Now, it has an uneven charge distribution because of this property called electronegativity. This is something you can actually measure, but that's not important for us. But electronegativity is a measure of electron affinity. Okay? So what does that mean? Well, an affinity, basically, if you have an affinity for something, it means you like something, right? I have an affinity for watches, So, I like watches. I probably spend way too much money on watches. I'm a watch nerd. Okay? So I have a high watch affinity. Fair enough. So electron affinity is an affinity for electrons. Okay? So oxygen has high electronegativity. That means it really likes electrons. And again, molecules don't have feelings. It has to do with stability, and there is a physics-based explanation for that we totally don't need to get into. But oxygen really likes electrons. Carbon and hydrogen, not so much. Electrons are great, but they're nothing super special. All right. So you can imagine you have this molecule here where you've got this oxygen here, and you've got these two hydrogens over here making your H2O molecule. And the oxygen really wants the electrons really badly, and the two hydrogens are like, whatever. So what happens? The electrons spend most of their time, because as I said, the electrons are kind of whizzing around the whole thing, whizzing around the whole thing, but they spend more time around the oxygen than they do around the two hydrogens. Okay? And so because of that, remember, electrons are negatively charged, the oxygen end of the atom builds up what's called a partial charge, right? And that's what this little letter means. It's a little lowercase Greek letter. This means partial charge. It's not a full charge, like a sodium ion, has a full +1 charge. A chloride ion has a full -1 charge. This is like a fraction of that. It's much, much less than a full charge, but it does have a little bit of a charge. So the oxygen molecule has sort of the oxygen side of a water molecule has kind of a weak negative charge. And then the hydrogen side of the molecule, you've got those two protons that are sitting out there that are, of course, positively charged. And the electrons are kind of spending most of their time, hanging out with the oxygen. So that side of the molecule builds up a weak positive charge. So partial positive on the hydrogen side, partial negative on the oxygen side. And so because of that, and again, opposite charges attract, we've said that multiple times, this weak positive is attracted to this weak negative, and they form a very, very, very weak temporary bond called a hydrogen bond, right? Now, hydrogen bonds are extremely weak bonds. We said before, a covalent bond is like a strong bond. We said like an ionic bond is like 1,000 times weaker than a covalent bond. A hydrogen bond is like 1,000 times weaker than an ionic bond. It's a very, very weak bond. It's not even so much to think of it as a weak bond. Just think of it as like water molecules like to stick to each other, right? Like they're sticky. Okay? That's what it's more like. Okay? If you have something sticky on your fingers, you put your fingers together. It's not as if, it's not super glue, right? But you can feel some resistance to your fingers pulling apart if you've got some sticky residue on it. That's the idea. So water molecules are like that. They tend to stick to each other. They tend to stick to other molecules. They kind of tend to stick to anything. And that stickiness of the molecule has to do with the formation of these hydrogen bonds, right? And they form those hydrogen bonds because of the difference in electronegativity, and that's why they're polar, okay? Now, a molecule that has an even charge distribution, where the electrons are sort of evenly split throughout the whole thing, is called a nonpolar molecule, right? Things like methane. Methane is CH4. It's a gas, right? Methane is nonpolar, right? It's carbon, it's hydrogen. Both of them have low electronegativity. So the electrons kind of just sort of smeared out everywhere. They don't build up in any one place. So you don't get the formation of these partial charges. Okay? This hydrogen bonding, this tendency for water molecules to hydrogen bond together and water molecules to hydrogen bond to other things, is what's going to give water all of its special properties, right? So we're at 15 minutes, so we'll stop here. We'll pick up with part 4, talking about the properties of water. Okay, we'll see you then.